Welcome back. In our last video, we looked at the universe we live in, and we showed how a new state of matter called black matter is formed by the extreme gravity of a black hole. And in this section, we'll examine where our universe came from at its very beginning, an event that we call the Big Bang. And we'll see that black matter and the black marbles that are made of it will play very key roles. But first, I want to take a closer look at the component of our universe that we call energy. We use energy all the time in daily life, and the kind we're most familiar with is called thermodynamic energy. And it comes in many forms: electricity, steam, chemical energy, and so on. We convert it from one to another to perform useful work. Well, here's an appropriate example of a thermodynamic system. It's appropriate because thermodynamics was first studied in the 19th century by engineers who were trying to improve the efficiency of steam engines. Now, the thing about a thermodynamic system is that it dissipates its energy. And we can see that here. The locomotive is dissipating energy through heat blowing out of the stack and steam coming out of the cylinders and the friction of the drive rods and between the wheels and the track. And as the system dissipates its energy, it runs down. And if we don't keep supplying new energy from outside the system, it will grind to a halt. There's another kind of energy in the universe that is so different that I call it by a different name. I call it E-energy. And it's created by converting ordinary matter into energy according to Albert Einstein's famous equation, E equals mc squared. The E in E-energy stands for Einstein, and E for E equals mc squared. As you probably know, M stands for matter, and C is the velocity of light. And since light moves very fast, C is a big number. So the formula means that a small amount of matter can be converted to a very large amount of energy. Now, once this energy is created, it becomes thermodynamic energy, and it can be infused into a thermodynamic system to replace the energy it's dissipating, to replenish it and keep it running. E-energy can be created directly from matter in a nuclear process. And the most familiar example is the sun. Every second, the sun converts about 400 tons of hydrogen to energy, much of which is radiated into space. Now, a small amount of it falls on the Earth, and this is sufficient to supply the energy needs of our planet. Some of it's used directly to warm our atmosphere and drive our weather systems and ocean currents, but quite a bit of it can be stored for later release. The most familiar way to do this is photosynthesis, where the energy is converted to chemical binding energy in carbon in plant foliage. And you can release it by burning it right away, or the dead foliage can stay in the earth for hundreds of millions of years and turn into fossil fuel. Now, once it's stored, it can be released in one of two ways: combustion and detonation. After it's released, there'll be less matter left over than you started with, and the matter that disappeared was converted into the energy that was released. This process is in accordance with the important law of our universe called the conservation of energy. We can convert matter to energy or vice versa, but the sum total of both remains the same. Now, combustion is a slow, steady release of the binding energy through a burning process, such as a quiet fireplace, but at times it can be a raging wildfire. Now, detonation, on the other hand, involves a sudden, violent release, and we need to look at this process more closely. Detonation happens when a substance that's become unstable, either accidentally or on purpose, it suddenly releases its binding energy. And the result is an explosion that takes place in a very short time, but it's not instantaneous. And during this short time, a lot goes on. Some energy is released as heat and light, but the major portion goes into expanding space and creating what we observe as a shock wave. The shock wave propels the nearby ordinary matter away from the explosion, which for most explosions on Earth includes air, which creates the familiar sound of an explosion. It also creates clouds of dust from nearby matter and the residue of the explosive material itself. It forms what I call an explosive formation. We see these all the time. Every time we turn on the TV, we see explosions from domestic accidents or munitions blowing up in war reports. And a good R-rated movie will have at least one or two big explosions with the shock wave throwing out debris and sometimes cars and tanks and human bodies. But they all have a very similar appearance. The clouds expand out in a roughly spherical shape if there's nothing nearby to distort them, but they'll all form uneven, expanding clouds that we recognize as explosive formations. Inside the explosive process forms a structure of walls and filaments and debris forming around empty voids. Now, these formations look pretty much the same no matter how big they are and whether they come from a single stick of dynamite or a 500-pound blockbuster or even a nuclear detonation. They'll form these similar explosive formations. Now, even larger events happen in outer space. Here's a picture of the Crab Nebula, remains of a supernova that occurred in the year 1054. The clouds have disappeared, but we can easily recognize the walls and filaments and voids left by a big explosion. The same structure can form in even bigger explosions. Now, here's a picture of the structure of our universe. It was produced by a computer simulation, but it bears an almost exact similarity to the structure that we observe in our telescopes. So this is a depiction of the biggest explosion of all time, the Big Bang that created our universe. Now, here's another picture of the Big Bang residue, and this one's the real thing. It's a picture of the cosmic microwave background as we see it today. The different colors represent very small variations in temperature that have been spread out over a very smooth sphere. They give the appearance of the residue of an explosive formation that is spread out over an extremely large volume. It looks like it was left over from something that exploded in the past, and we just have to figure out what it was that exploded. And that's exactly what I'm going to propose in black marble theory. And not surprisingly, I'm going to suggest that the universe we see is the result of the explosion long ago of a black marble. Explosive formations all look somewhat similar, but no two are exactly alike. Nevertheless, they all produce two kinds of energy. The first is the radiation that produces light and heat. But over half the energy is released as what I call expansion energy. This is the energy that creates the blast or the shock wave. Now on Earth, it slams into the surrounding air and produces the familiar sound of the explosion. And it also imparts kinetic energy to surrounding objects and the remaining unexploded explosive material. The explosion is a chaotic process, and the dust and smaller particles are blown out in the familiar explosive cloud. And the debris is scattered into the walls and voids and filaments of the explosive formation. So let's keep that in mind in the next video as we take a close look at the Big Bang and discuss the history of our universe from its beginning up to the present day. All of these processes will play important parts in the theories that deal with the past and future of the universe. And that's where we're headed in the next video as we discuss the evolution of the cosmos and the perspective offered by black marble theory.